Okay, I think I'm there. So this is the last talk of this conference, so I should say how much I have enjoyed it and found it stimulating. And I'd forgotten after this period of COVID how sort of exhausting actually conferences were, but I think this is a very good way after the COVID era to sort of restart research. So maybe we should all thank the organizers, Christoph, David, Harald, Gregory and Satya. Give them a little clap. Okay, so thanks for their efforts. Okay, I'm giving a talk on stochastic resetting. So already in this meeting, we've had a few references to resetting, and there was a very elegant and clear talk this morning from Shlomi about it. So what I was intending, and if you notice, my title on the sheet was sort of to give an overview and review of everything, and I realized this was a little bit ambitious. So instead, my title is How to Avoid Wandering Off in the Wrong Direction. And hopefully that should become apparent from the talk. And so I would just limit myself to trying to give a sort of rudimentary introduction to the ideas of resetting, and then just talk about some recent things and not try to be comprehensive, because it's really, although there's lots of interesting papers on resetting, it's just very difficult to keep up with them all, and I don't think I can do it justice. So last night I tried to read lots of papers, and essentially I wandered off in the wrong direction and didn't get anywhere. Okay, so yeah, so actually Shlomi gave a nice introduction to the idea of resetting, and I usually motivate it by search processes, and I promised myself I wasn't going to tell this story, but actually this is the story I usually introduce resetting to, and it's about how does one search for lost keys. So back in Edinburgh, I used to live in a tenement flat, so for those of you who knows what that means, they're sort of Victorian apartment buildings, and they're good, solid flat. And I had a good, solid front door that was a wooden door, and next to the door there was a hook where the keys should be. And also underneath the hook there was actually, in those days I had an old telephone landline and a little table there. And so in the morning when I'd want to go out to work, I would go to the door and go to the hook where the keys should be, and of course the keys were never there. So then what do? I kind of started to sort of look around on the table by the hook, by the door, to look for the keys. They're not there, so I would then wander off into the back room, the kitchen, and look there for a bit, and then somehow wander into the front room. And at some point I would ask myself, what am I doing here? Getting a little bit old and memory's going, and then I'd say, yeah, okay, I'm looking for my keys, but I'm not finding them. So what is a good thing to do? And I think a reasonable thing to do is to say, okay, let's go back to the beginning and start the search again, where the keys should be. And that's basically it. So that is a strategy for a search. If you get stuck after a while, go back to the beginning and start again. And the question is that a good strategy? And also in that little example, my rummaging around is kind of meant to mimic a short-range search, like a diffusive search, and then making big moves to the front room or the back room. These are long-range moves, and this is generally thought to be a good strategy, mixing up long-range and short-range move, and that's an intermittent search strategy. So I won't go, oops, somehow that's changed. I won't go into all the details of search problems. The idea is this resetting a good strategy? Isn't working too well. Okay, so Shlomi also has sort of put this kind of question into a more general context. So I'll just mention here the complex, I think Shlomi mentioned this in his talk, so some complex chemical reaction. So you have some enzyme, it binds to a substrate and to give an ES, and that kicks off a whole complicated stochastic chemical process where eventually some product is produced, but because it's so complicated, it can get stuck. And then a good thing to do is to unbind the enzyme from the substrate and start all over again. And that can actually increase the productivity of the product. So the basic idea, sorry, I should have said this, the very general idea of resetting is that you're cutting off errant trajectories that go off in the wrong direction. So coming back to my example of me looking for my keys, an extreme example would be if I was really dozy in the morning, looking for my keys, and I somehow wandered out of the front door and wandered down the street looking for them, then I'm not going to find the keys there. And so that would be some errant trajectory that it would be good to cut off straight away and then set back to the origin. So these are examples where, again, we're cutting off errant trajectories. Okay, and also we mentioned restart programs when some computer algorithm is looking for a solution of a complicated optimization problem. It's quite often a good idea just to restart at the beginning. And so the general idea of resetting or restart, I mean, this review here gave some historical perspective. You can argue about where the sort of initial precursor is. And I would say probably you could trace it back to sort of some models of queuing theory and population dynamics, where naturally when you clear the queue, then you're resetting. Or if you have some catastrophe in the population where the population size goes back to 0, that's like a reset. So, the idea has appeared in a variety of contexts. That's all I want to say. So that was the introduction. So this idea of cutting off errant trajectories. And the rest of the talk, I want to start by, I will use the model of diffusion with resetting. And I'll try and give a sort of hands-on talk with some sort of equations that you should be familiar with. So I'll recap diffusion, and then move on to, oh, actually, I haven't said resetting there. Introduce some of the ideas of resetting through a renewal approach, which, I mean, everyone has their own preferred approach to do calculations. In the end, I think Satya and I sort of feel the renewal approach is quite quick and elegant. Other people have other approaches, but I'll focus on renewal. And then I'd like to mention a generalization to, instead of just resetting to one position, you choose a sort of random position in the past and reset to that. And finally, I'll get onto the recent developments, but only just a few of them. I can't do them all. Okay. So let's start with something we're all familiar with, just a diffusion equation. So for the moment, there's no resetting. This is kind of easy peasy stuff, just to sort of gently break you in. This is a diffusion equation for the probability density of being around point X, having started at X0, first order in time on the left, second order in space. And of course, if we have some initial condition, let's say delta function at X0, the initial position, then the solution is just a Gaussian. And that's great. So if we're on an infinite system with no boundaries, then this probability distribution just gets wider and flatter. And there's no stationary state. Okay, that's all simple stuff. An interesting thing, this is actually the forward, if you like, diffusion equation, because the spatial coordinate is the final position. We can also write down a backward equation where here the spatial coordinates that's varying is the initial position. And the nice thing about diffusion is that it's the same equation for both, right? So often you have to be a little bit careful, but for diffusion, it's just the same equation. And this backward equation is actually very useful for first passage properties. So first passage, we're interested, let's say, in the first time to reach the origin. So we can think of that as an absorbing target at the origin. So when I say absorbing, it's sort of, you have this diffusive particle, it gets absorbed when it touches the origin. Yeah. So we can fix that by putting the boundary condition that this probability density is 0 when either of the, the initial or the final spatial coordinate is 0. And then we can look at the survival probability, so just integrate over all the final positions. And then the cool thing is that for the backward equation, and when we integrate over the final position, we still have a diffusion equation. So this Q is the total survival probability, and it just has a diffusion equation if you solve it with the right boundary conditions. Just to be clear, what are the boundary conditions? Yeah. So again, if x0 equals 0, then it doesn't survive, it's absorbed straight away, so that's always 0. And at time 0, then it survives with probability 1. So they're the boundary conditions. If you solve the diffusion equation with those boundary conditions, you get an error function. And when this argument becomes small, so t is becoming large, this, just to expand the error function, it goes like 1 over t to the half. So the survival probability decreases with t. So it goes to 0 after sufficient time. So that means that the particle is always absorbed with probability 1. But the weird thing is that if you calculate the mean time to absorption, which we'll call, well, okay, here I've called it mean first passage time, also known as mean time to absorption, mean hitting time, lots of names. You get this from this survival probability by, okay, you get the probability density for absorption by taking the derivative. Then if I integrate with respect, multiply by t and integrate, I get the average time to absorption, and this clearly diverges. So although you get, it finds the target with probability of 1, the mean time to find the target diverges. So that's not a very good search strategy, because you're going to have to wait, on average, a very long time to find a target. So that's the thing. A purely diffusive search is not very efficient. That's the message there. And so we're going to expedite that by introducing resetting. So I'm just going to go through the same stuff now with resetting. So the simplest example of resetting is just saying that there's a Poisson process. So just there's an external, the bell rings at exponentially distributed waiting times. And when the bell rings, the particle just goes instantaneously back to the initial position, x naught. Now, obviously, you can generalize that to a non-Poissonian, so a different distribution of waiting times, or you can think of a distribution of sites to reset to. This is the simplest vanilla example, where it's instantaneous Poissonian resetting to x naught, and the rate, so the probability per unit time is r. Yeah, this is the rate of resetting is r. So let's just start with the forward equation. Remember, that was the diffusion equation. Just to get the hang of it, the resetting, what that means is that we lose probability from all positions x, so there's a minus sign there, and all that probability goes into position x naught, so we get a source term at x naught. So they're the new things. That's simple enough to solve. Okay, in the stationary state now, so the limit t goes to infinity, we can, if the left-hand side is 0, we can solve that, and we get this Laplace distribution, which came up in Ellie's talk. So it's a sort of double-sided exponential. So that's all simple stuff. And what we have now is actually it's a very simple example of a non-equilibrium stationary state. So we've got this distribution. And the idea is that the probability current, we have a diffusive probability current that diffuses out from the center, and then the resetting takes probability back. So we get circulation of probability. So it's a very simple example of a non-equilibrium stationary state. And this is the other reason for studying resetting, is to generate non-equilibrium stationary states by never letting your system relax. You're always resetting it to the initial condition. Okay, now, so that's the basics. We've seen, we've seen the non-equilibrium stationary state. We want to see now how the survival probability changes. And to do that, I'm going to use a renewal approach. But let's first of all just write down, forget the absorbing target. Let's just write down the probability with resetting on an infinite system. I should have said I'm presenting here one-dimensional system. You can do all this stuff in higher dimension. It just gets a little bit more complicated, but it's basically the same. So the R here means that we're in the presence of resetting. So we're going to go from x naught to x in time t. And we can do that basically if there's no resets, and because it's Poissonian, the probability of no resets is e to the minus rt. And then p0 is just the propagator in the absence of resetting. So remember, for diffusion, that was just the Gaussian. That's a probability without any resets of going from x naught to x. And then we can say, well, there were some resets, and we can integrate over the position, or the way I've done it here, t minus t primed is the time of the last reset. So the particle, when it gets reset at t minus t primed, it goes back to x naught, and then it just has to get from x naught to x in time t primed. So there you go. So it's, and once you get that, initially you have to sort of strain your brain thinking about that, but after a while it becomes second nature just to write down these renewal equations, and they become the easiest approach. So clearly the stationary state there, we get when t goes to infinity, this term vanishes, this becomes integral from 0 to infinity. And so that actually becomes the Laplace transform with Laplace variable r of the p naught, the propagator. So that's a result that Shlomi mentioned. The stationary state under resetting you get from Laplace transform of the process without resetting. And you can also use this equation, I don't have time to get into the details, to look at the relaxation to the stationary state, which is very interesting. You have to, so Gregory and Satya can tell you all about that. You have to sort of look at the saddle point of this integral here, and you get interesting transitions. Yep.
Normalization of
they all are.
R is an arbitrary number, right?
No, they all are. Okay, so
PR star, right?
No, PR is normalized.
PR, and as a result, PR star.
Yes. So let's say we've started with P naught normalized, and therefore you can check that PR will be normalized because we don't lose any probability, and so everything is normalized.
So P0, why is P0 not normalized?
It is normalized.
It is.
P0 is the Gaussian.
Okay.
For the case of diffusive process. Here we're writing it very generally, so it could, we don't have to have an underlying diffusive process. It can be whatever you like, but yeah, we should have it normalized. Yeah. Anyway, let's move on. So now this is what we want to do, calculate survival probability. So we're going to use again the renewal approach. It's a little bit, we have to again think a little bit here. So we're dealing with survival probabilities this time. So we get the same idea, the probability of surviving up to time t, having started at x0. There will be the term coming from no reset events, which happens with this probability here, e to the minus rt. So that's just the Gaussian, the survival probability for diffusion. Or there could have been some resets, so we integrate over the position of that last reset. And then you have to think, well, we need to have survived, so that time of the last reset is t minus t prime. So we need to have survived up to time t minus t prime with resetting. And then, okay, sorry, I should have said this is the probability that there's no further resets. And so we have to survive for the final time region t primed without resetting. So there's a Q naught there. Again, but once you've written that down and got it right, then life is very simple because you just take the Laplace transform, and this is a nice convolution, and so everything just falls out. In terms of Laplace transform, this factorizes, and you get the final result for the Laplace transform or the survival probability with resetting in terms of the Laplace transform without resetting, but with Laplace variable involving R. So this is a nice result, and it's quite general. Okay, so good. So let's just look at the particular case of diffusion with resetting to see what happens. Yeah. So for diffusion with resetting, this is a known classical result for the Laplace transform of the error function that I showed you earlier. So let's just take that as given. We just substitute it in, and then we end up getting this expression, the Laplace transform of the survival probability. And one very useful thing, if we just set s equals 0, this is a very general thing, you get the mean first passage time. Okay, it's easy to see that. I won't drag you through the details. So setting s equals 0, we get the mean first passage time, and it comes out as that. And there you go. So that was quite painless. And let's have a look at this expression here. So this is the same equation I had before. So we know that when r goes to 0, the mean first passage time should diverge. And if you look at this carefully enough, yeah, it's going to diverge like 1 over r to the half. And Also, you get a divergence when r goes to infinity because of this exponential up here. So, and that one is easy to understand. If you're constantly resetting, the particle never has a chance to get anywhere, so it's never going to locate a target. And in between, there's just a unique minimum that you can calculate, dt by dr equals 0, nice and simple. That is, the equation simplifies if you introduce a reduced variable y. So what is y? Remember, x naught, we're resetting, sorry, the target is at the origin, we're resetting to x naught. So that's actually the distance between the target and the resetting site. And then 1 over this is actually the typical time, or no, the typical distance the particle diffuses between resets. So it's the ratio of two distances, the distance to the target and the typical diffusive distance between resets. So the idea is if you tune this appropriately, this y variable, and the optimal value is actually 1.59, then you minimize the time to find the target. So that was sort of, yeah, the main result. And this is a sort of typical property that there is going to be an optimal resetting rate. Now, of course, if you could argue, well, you know, to get this optimal rate then and use this formula, we need to know where the target is. So it's sort of the theoretical optimal rate. But the point is you can vary the resetting rate to change your performance of some search. Now, I just make a detour and discuss actually something that Shlomi mentioned this morning, which I find interesting. So right at that optimal R star, it turns out that the coefficient of variation, so this is the standard deviation of the mean first passage time over the mean, standard deviation of the first passage time over the mean first passage time for this particular value, R star is equal to 1. And that's a universal result. And that also provides a criterion for the resetting to expedite or speed up the process. So basically, okay, roughly speaking, the criterion is that in the absence of resetting, if this coefficient of variation is greater than 1, then you can improve the time to find your, or reduce the mean first passage time by turning on a resetting rate. Okay, so then, yeah, so we've got, so what I've discussed so far is the mean first passage time, and to show how it becomes finite with resetting. We did the calculation for the Laplace transform of the whole resetting, survival probability. So let's have a look at that. The Laplace transform, this is just the formula I had before. Now, if you want to invert the Laplace transform, you get the large time dependence by looking at the singularities. What you see is that you get a non-trivial pole at this particular value of the Laplace variable S. And what that will imply is that the long-time behavior of the survival probability now decays exponential. So S naught here, look, is negative the way I have to find it. But you get this non-trivial exponential decay. So what the resetting has done has changed the power law decay for diffusion into an exponential decay. And I find this pole quite interesting. It's not, in all these papers that have been published, this pole has never really been sort of analyzed, but that is the large time, that does give the large time behavior. Okay. Right, so also, yeah, the point of this slide is also to make the connection with the title of the conference, which is, okay, extreme value statistics. So we've got this exponential decay of the survival probability. If I take this variable here, remember, which was the ratio of two, well, it's a dimensionless variable, that's the ratio of two lengths. I take it very large. So this means the distance to the target is much larger than the distance diffused between resets, which means typically there's going to be a lot of resets before the target is found. Take that large, then this actually, S naught just becomes minus R exponential minus Y. The survival probability is an exponential of an exponential. And so for those of you who are familiar with extreme value statistics, that's basically a Gumbel distribution. So why does extreme value statistics come into this? I think it's easiest if I just draw a picture. You can get the idea. No. So what I'm drawing here is just a typical trajectory. So this is time, and we've got our x naught, our initial, and yeah, usually I should have said in this talk, I'll just assume the resetting position and the initial position are the same. So that's x naught, and then we've got our target at the origin. And so the particle is diffusing, then it gets reset every so often, and then it diffuses off. And so to have survived up until some time t, it's typically going to, on average, there will have been RT resets. And in all of these reset epochs, then the particle shouldn't have gone as far to the left as to reach the origin. So the maximum displacement to the left should be less than something for a large number of, I should say that these epochs are independent, a large number of independent random variables, and so that basically will give you a Gumbel distribution. Well, R is in Y, so it's okay. Yes. Yeah, sorry, I didn't explain that too clearly. Got it? Yeah. So it's like RT is the number, is N. Yeah. Okay, so this is what I've said. Maybe I can say it better again. On average, there are RT resets. For each reset, process is renewed. And yeah, and the particle must not reach the origin in any reset. So the maximum dispersion to left in all the resets should be less than something, and that's just Gumbel statistics. Well, okay, with an appropriate survival probability. Right, now this is, okay, so that was the sort of basic of the talk. I'd like to mention this aspect, and when I've given sort of related talks before, I feel that I haven't explained this too well, so please shout if this is not clear. So far we considered, for diffusion, resetting to the initial position. Now, instead you can think of resetting to some time that you select from the past. So if you're resetting to the initial position, you're going to time 0. Instead, you could go to some time less Tor, which is less than the present time t. But you can pick Tor according to some distribution. And we'll call that, right, it depends on Tor, the time that you're going back to, and t, the present time. And we call that the memory kernel. And again, just to check we're on the same page, the forward equation is just diffusion. We get a loss term from resetting. And this time the resetting goes to the position at time Tor. So we've got the probability density of choosing Tor, and then the probability of being at x at that time Tor. You have this more complicated equation. And to simplify things, this memory kernel depends on the time you're resetting to and the present time. But to make it simple, it's basically, we say it's a function of the resetting time, and then we normalize this. Okay, so that if we integrate from Tor, going from 0 to t, we get 1. That's sort of the simplest structure it could have. Is that clear so far? Because that's, I think, often throws people. So we're just resetting to some random time that we select and the position at that time. So the first question, so remember for resetting to the initial condition, we got a non-equilibrium stationary state. The question is, when do we get some stationary state by doing this? And what you require is this phi here. Tor times phi should go to 0 as Tor goes to infinity. And under that condition, you will get some non-equilibrium stationary state. And it may not be the exponential form. You have to work it out. Then, if you don't have a stationary state, then you might think, well, it's going to be like the usual diffusion, that you have a Gaussian that's just getting wider and flatter. And indeed, you'll get a Gaussian, but the interesting thing is that the width of the Gaussian can have a different time dependence than diffusive scaling. So here I just present. Say that again. No, phi is just a function. No, this is a probability density k, because I've normalized it. You got it? Yeah. Okay. So again, so just looking at this, I need to normalize. Tau can go from 0, the initial condition, or the final position at time t. So when I integrate this, I just get 1. So that's a probability density. Yeah. Yes. Yes. Yeah, you can. Okay, that is a very good point. That's a subtle point that you need to convince yourself that when you average, it's basically a linear system, and you can put the probability in there. It's not obvious, and it's a subtle point. And so Denis Boyer basically demonstrated that that's valid. Yeah, so the question is then, yeah, as I said, we can get interesting dynamical behavior when we don't get a stationary state. And we can choose different behaviors for this function. So the first one, if I have phi of Tor, now it's increasing exponentially, so A is positive. So remember, Tor is the time we're going back to. So if this is peaked at the present time t, that's sort of like diffusion. And so we get diffusive behavior, and as A, when it gets more and more strongly peaked, A goes to infinity, we get the usual 2 dt. But when A is finite, then we change the diffusion constant, but we get diffusive behavior. Then we can choose something a bit more exotic, like a stretched exponential. Again, it's peaked at the present time, but it's decaying it's more slowly than an exponential. And then, interestingly, we don't get diffusive scaling, we get anomalous scaling. The variance is t to the beta. And then we can put in a power law, and if the exponent is greater than -1, we'll get logarithmic. Well, so the variance goes log t, so the standard deviation goes like log t to the half. And that includes the case where we just randomly pick a time from the past when it's a flat distribution. That would be alpha equals 0. Then even more exotic is if we just choose the marginal case of 1 over Tor. Remember, so if the power is less than -1, we don't get a stationary state. So this is the marginal case where we just get a stationary state. So we don't get a stationary state. Then the width grows really, really slowly as log Tor. So very, very slowly does the distribution broaden. So I find that interesting that you can, fundamentally change diffusive behavior, which is a fundamental dynamical scaling. You can get all these different scalings just by simply having some resetting process, moving you to a previous position in the trajectory. Was that clear? Oh, sorry, go on. Okay. Yeah, I haven't yet. So I'd think about that. I think you're right, yeah. So if you had a long, right. So far it's instantaneous resetting. You can easily put in a waiting time. Sorry, is it the waiting time for do the reset or between resets? Yeah. Yes. Okay. Sorry, Rob, did you have a question? Yeah, fine. Okay, so good. So anyway, just a summary, that was meant to be the rudiments. I don't know, how much time do I have left? 5, okay, so it has to be very fast. So this is just to emphasize these, resetting to initial condition, you can generate non-equilibrium stationary state. And that's, as we'll see in the sort of applications, this is one facet of resetting that is appealing to non-equilibrium physics, to generate non-equilibrium states. Okay, that's what? That's meant to be resetting to a random time. We can get different scaling for a diffusive process than the diffusive scaling. And in terms of mean first passage time, resetting renders, for diffusive process, it renders finite the mean first passage time. And survival probability goes from a power law to exponential. And we've got connections to extreme value statistics. And then, if you like, in the early papers, there's a bunch of other stuff that was done that I haven't had time to discuss here, namely a whole bunch of diffusive particles searching for a target. So in the time that remains, actually, let me just try and give an overview of recent developments. So, yeah, as I said, I was looking through the literature last night, and I've tried to sort of, people that are here that have done nice work, I've tried to mention it. So I do apologize if you've missed out, but I think the most important development is basically experiments, and there's resetting experiments. 2 groups, so Tel Aviv group, okay, that's the first author. I guess Yale Rochman is the group leader there. And then Sergio Ciliberti's group in Lyon. And they're both using optical laser traps. They have different protocols and different techniques, and I don't know the details, but they're both doing resetting experiments, which is great. Yeah, go on. In what sense? Oh, I see. Yeah. Okay, in terms of the search for, no, absolutely. No, I'm with you. I got the wrong facilitated diffusion. You're talking about, proteins binding on DNA. Yeah. Yes, absolutely. No, this is the same scheme of things, intermittent type searches. Yeah. So experiments, there's been thermodynamics of resetting. As I said, the instantaneous reset is sort of rather artificial, but you can sort of think of thermodynamic cost of resetting, and Udo Seifert worked on that. Fluctuation theorems also have been developed by Arnab Pal. Quantum dynamics, I guess, is the next frontier, and Satir has got in there first with some colleagues. And then, you can go around and create non-equilibrium stationary states by resetting, so you can explore the effects of resetting in a variety of different contexts. So fluctuating interfaces under resetting, there was Amit Gupta and Satir and Gregory. We got into resetting run and tumble particles, and the interesting thing there, the run and tumble particle has a position and a velocity, so you have 2 parameters to reset, so double the fun, and you get interesting things happening. And then resetting, so Erna and Anupam have been resetting the simple symmetric exclusion process. And I saw last night, and Chris Mass was telling me this morning, that he's resetting photons by sort of resetting the frequency distribution of photons. And then we have many particles under resetting. As I said, I didn't have time to discuss some of the early stuff, but Baruch has been looking at Brownian bees and sort of resetting, having a bunch of particles and resetting the furthest one away. You get non-trivial properties there. So that's all great. And then if I have any few minutes left, I just want to mention I've sort of been doing a lot of admin the last 3 years. So just a couple of things that we've managed to do on resetting. So this was with Georgia, who was an MSc, Georgia Calvet, who's an MSc student. Actually, interestingly, she went off and after her MSc, she founded a company making bespoke stationery. And so one day, sort of a parcel came through the post, and she'd sent me a nice bespoke notebook with Professor Evans embossed on the front, which I was very happy with. But it's now full up of calculation, it's full up of teaching. Anyway, so she was interested in the idea of protein searching for targets. And often for DNA lesions, when you've had some radiation damage the DNA, you get a cluster, so a bunch of correlated targets that are all together. And then we were interested in, well, if you have sort of a cluster of targets, what's the, will this resetting be a good way to find all the targets? Because to heal the DNA, you want to find all the targets. So we just actually then considered a very simple system of, so this is my very poor figure. This is meant to be 2 targets, and we have a resetting, so this is where the protein molecule can bind, then it has to find both targets. And it kind of resets with the rate R. But the idea is that we want to find the mean time to find both of these targets at XL less than 0 and XR. And then this is what Georgia produced after, by the way, you can do these calculations for multiple targets. It's quite fun. Won't give any details. But her final results showed this is the mean time, and this is actually as a function of the position of this target. And the weird thing is, if you move this target further away, your intuition would say that the time to find the target should get longer, but actually it gets shorter. And the reason is in the model, okay, so there's a conundrum there, but the reason is in the model, when you find the target, then the protein heals and it goes back to the original binding site. So if you like, that's a free reset. And so if this target here is right at the origin, it gets found straight away. And then the system just reduces to trying to find this target, and with resetting with rate R. However, if this target is out here somewhere, then initially it acts as a kind of backstop. And it introduces an additional resetting when this one is found. And that overall reduces the mean time to find both targets. So put simply, if you have a cluster of targets that can actually, and suitable dynamics, that can actually reduce the collective effect, which reduces the time to find one. And so the final thing I did want to mention, I don't have much time, I've mentioned that we just resetting with rate R for Poissonian resetting changes the diffusive survival probability, a power law, to an exponential. So one question is, can you get other forms? I mean, can resetting do other things and give you other forms for survival probability? And without getting into details, we just recently, with Gregory and Satya, we've published some, okay, it's motivated by predator and prey. So you have a prey that's diffusing around a bunch of predators. When the prey meets the predator, it can perish, and that will be the game over, or it can survive and reset back to the origin. Now, as time goes on, basically what happens is that the predators, because they're diffusing, they become more diffuse. And so effectively, the separation between the predator and prey, when it goes to 0, you have this encounter and a probability of survival. And then when you reset, the typical distance between them is reset to something that that increases with time. And this effect is enough to change the diffusive survival probability to some exponent that's completely non-trivial, and okay, it's a solution of this horrible equation, but it depends on parameters p, the probability of the predator getting eaten on encounter with the prey. No, the other way around. The prey getting eaten on encounter with the predator, and also gamma is kind of the ratio of the diffusion constants. But you can, anyway, the point is you can change the survival probability in a non-trivial way. And yeah, I think that is all I wanted to say. Thanks.